Hi everyone, welcome to our event. This event is brought to you by Data Talks Club, which is a community of people who love data. We have weekly events. This is one of such events. So if you want to find out more about the events we have a link in the description, so check it out. And actually this number is not up to date, so I should update it right now. Yesterday I noticed that it's 15,000 subscribers. That's awesome. Thanks everyone for subscribing to our channels. But if you haven't subscribed to our channel yet, so now you can do this. There is this red big button below the video. Click on this button and you will get notified about all our amazing videos like this one today. And we have a Slack community where you can talk to other people, to other data enthusiasts, so check it out. And we have a free course about machine learning engineering starting soon. So there is a link in the description too, check it out. And then finally, during today's presentation, you can ask any question you want, and we will cover these questions after the presentation, right? Or should I, or it's okay maybe for you if I interrupt you and ask them? What's the preferred way?
If it's relevant to what I'm talking about, relevant. Maybe it's okay. Better.
Yeah, and if it's not, we will cover them at the end. Okay, I guess that's all from my side. Now the floor is yours.
Thank you. I'm going to share first. Can you see the blue screen now, or what are you seeing?
Not yet. Oh, now I can. Yes.
All right. Okay. Welcome everybody. Thanks for the opportunity to talk today about feature selection in machine learning. I'm going to first start talking about different algorithms that we can use to select the features, and then towards the end I'm going to make a few demos with how we can implement these methods with Python. A few words about me. I'm a data scientist. I worked in finance and insurance, building models to assess credit risk and to prevent fraud. I'm also an open source Python developer. I actually am the maintainer of one open source Python package for feature engineering that is called Feature Engine. And at the moment, I'm also teaching machine learning online through courses and books. And the talk that I'm going to give today is related to my latest book, Feature Selection in Machine Learning, and you can find it here at this link. A few things about this talk. If you want to find the slides and also the code that I'm going to show later on, you can find it all together in this repo. So without delay, I'm going to jump into feature selection. So feature selection is the process of selecting a subset of features to train machine learning models. So in essence, we have huge data sets, and the feature selection, what we're trying to do is to reduce the number of features to a subset of features that produce ideally good performing machine learning models. Now, when I talk about feature selection, I often get the question, why are you not introducing principal component analysis? And the thing is that feature selection is not the same as dimensionality reduction. Feature selection algorithms do not change the nature of the features. So what we do when we select features is we just select subsets from the total pool of features without really changing the nature of the feature. And this is very important because this is what allows us to then understand what our models are telling us. Whereas techniques of dimensionality reduction, what they do is they create new features by combining the existing features in the data, so then the interpretability of those new features is a little bit harder. This taps into the question of why do we select features? Why do not we just use everything that we have in the data set? And there is a very practical answer to this question, and is that simpler models, that is models with fewer features, are easier to understand, they run faster, they use less storage, and they are easier to maintain. So what does this all mean? When we create machine learning models with the aim of using these models in an organization, there are certain things that we need to tick. For example, when building models to assess credit risk or to prevent fraud, Some of the decisions of the models are going to be automatic, but some others are going to be referred to people, and these people need to make the final decision. And it's easier for them if they understand why the model is suggesting to take this or that decision. And it is easier to understand or to interpret a machine learning model if it's based on 10 features than if it's based on 1,000 features. Because we humans are able to cope only with so much information. The other thing is that algorithms trained on smaller subsets of features, they run faster and they use less storage. We need less storage to store 10 coefficients, for example, than to store 1,000 coefficients. And also this is easier to maintain because when we put a model in production, the story doesn't end there. We need to monitor that model throughout the life cycle of the model. So as long as we're using the model, in general, we monitor what's going on. This means that we're going to monitor the input, the variables distribution, for example. And one thing is to monitor 10 variables, and something very different is to monitor 1,000 variables. So the aim of feature selection is to produce simpler models that we can understand, put in production, and then maintain all throughout. And this is particularly true for the industries like insurance, finance, when we have to understand why a model thinks that an application is fraudulent, or why we think that we need to give or decline this loan, and so on. So we know now why we select features. The next question is, how do we select features? And the thing is, there are many feature selection algorithms out there because there are many data sets and there are many variables. And some algorithms are suitable for some situations and some type of data, and some algorithms are suitable for something different. And it is also true that there are many optimal feature subsets. So for example, if we're using 5 different feature selection algorithms, it might be the case that we end up with 5 different feature subsets, and all of them produce models that are more or less equally performant. And this is fine because in our data sets, there are feature redundancies. This means that we have features that are more or less the same, identical, or correlated, or that the information of one feature already tells us enough about the probability of the values of the different features. So it is not rare that we encounter many feature subsets, or at least more than one, that will return good performing machine learning models. And the other thing that is good about this is that there are 3 at least Python open source libraries that implement many of the feature selection algorithms out of the box. And these libraries are, for example, scikit-learn, MLextend, and Feature Engine. And what does it mean that they implement these selection algorithms out of the box? Well, that all the logic that I'm going to cover, for example, in the coming slides, is already baked into the implementation of these algorithms, which means that we only need to call the selection algorithm like we import, for example, random forest from scikit-learn, and then with the methods fit and transform, we already carry out the entire feature selection search. So, okay, there are many feature selection algorithms. Where do we begin? I would say that when we take a data set, particularly if it is a big one, the first step is to remove useless and redundant features. And these include features that are constant. These are features that have one value in all their variables. Features that are duplicated are basically identical variables, and also features that are quasi-constant. When quasi-constant features are features that show the same value in 99% of the observations, and in very many cases, removing these features doesn't really have a dramatic effect on the performance of the model. And there is an example in one KDD competition in 2009, where the competitors, actually the 3 winners, by removing this type of variables, managed to reduce the data set from 3,000 to 1,000, give or take a couple of hundred features. So this method, as silly as it sounds, is really powerful to reduce the size of the data sets at the beginning. Now, after this, what can we do? Yes, before this, I wanted to say that these methods can be implemented with scikit-learn and Feature Engine. But after removing constant features and duplicated features, what can we do? Well, there are various feature selection methods, and these methods are grouped into 3 categories that are based on the characteristics of the algorithms. We have filter methods, wrapper methods, and embedded methods. And there are, of course, a lot of algorithms that do not fall in any of these categories, so I will put them under the new category, which is other methods. And the good thing about this is that the Python libraries that we have already cover many of the algorithms that we find for every group. So scikit-learn has 3 or 4 methods to carry out filter methods. Wrapper methods can be carried out with scikit-learn on MLX10. Scikit-learn also offers embedded methods, and Feature Engine basically provides everything that is not available anywhere else. So filter methods, what are these? Filter methods are also known as ranking methods because what they do is they basically rank features with some criteria, and then they are going to select the highest ranking features. And there are many ways in which we can rank features, and the most perhaps commonly used or the most well-known are the ranking of features utilizing statistical tests. And the ones that we have available in scikit-learn are chi-square, ANOVA, correlation, mutual information, and also the variance. The variance is one way of ranking features based on the variability of the feature. So we have the example of the constant feature, that one has 0 value, and it is fair to assume, although not always true, that the higher the variability of the feature, the more predictive it could be. So statistical tests, they all have their characteristics and they need to be used with caution. Chi-square, for example, is suitable for categorical variables. So when we want to select categorical variables and we have a categorical target. ANOVA is suitable when we have continuous variables. So we want to select among a pool of continuous variables and we have a categorical target. And correlation is suitable when we have continuous variables and continuous targets. So here, straight away, we can see the problem that if our dataset has a little bit of continuous and a little bit of categorical variables, which of the tests we use? It's not a simple answer to that question. All statistical tests, they basically test the null hypothesis, which is the negation of the difference. In the case of chi-square and ANOVA, they are going to test the hypothesis that the distributions of the variables are the same across the targets of across the classes of the target. And correlation is going to test the null hypothesis that there is no association between the variables and the target. All of them produce a p-value, which is the probability that the null hypothesis is true. So the smaller the probability, the less likely that the null hypothesis is true. So the more likely that there is a difference between the distributions, or there is an association of the variable with the target. Therefore, the smaller the p-value, the more important the feature. And this again needs to be taken with a grain of salt because statistical tests are susceptible to the sample size. So big data sets will inflate p-values. This means that we will have very small p-values when we actually don't really have a big difference. And the other thing that is important is that statistical tests make assumptions on the data. So for example, ANOVA assumes that the variables are normally distributed. So if this is not the case, then how much we can trust these p-values is a question. So I won't have time to explain all the statistical tests in detail. So my idea was to explain one method from each of the filter, wrapper, and embedded methods. So I chose chi-square. Chi-square compares the distribution of the categories of the variable across the classes of the target. So for example, if we have the Titanic dataset, we have the variable gender with values female and male, and then we have the target that is died or survived. And we can create with this what is called a contingency table with the observed distribution. So this is what happened in the Titanic. And here we can see that we have more or less half women that died and survived, but here we don't have half male that died and survived. So we can suspect that there is an association between gender and survival, meaning that if you were male, you were more likely to die. in this sheet. Now, the chi-square test compares the observed distribution versus one expected distribution, that is what I expect to see if there was no association. And this distribution is calculating based on the joint probability, so it's going to be calculated by the total of the row plus the total of the column divided the total number of observations. So if we look at this one here, to calculate how many individuals I need to place here, I need to multiply the total number of people who died by the total number of female and divide by the total number of observation. And this is how I obtain this value. Then I subtract the observed, the expected from the observed. I put it in this chi-square statistic, and I do the same for all the cells, and I obtain this value of the chi-square. And this chi-square follows a very well characteristic and very old well-known distribution, which is the chi-square distribution, which varies according to the degrees of freedom. And the degrees of freedom are given by the number of columns and the number of rows. So in this case, it's going to be 1 degree of freedom because it's columns minus 1 times rows minus 1. So if we obtain a chi-square value of 4, we come here, we follow number 4, and then we obtain here the p-value of 0.05, more or less, which means that the probability that these two variables are not associated is really low, which means that most likely there is an association of the variables. Therefore, my categorical variable is predicted. So if I repeat this for all the categorical variables that I have in my data, I can then obtain p-values for each of them. I rank them, and then I can select the top ranking variables. Now, there is something that is quite interesting, is that the scikit-learn implementation of chi-square is not correct. And this is a known issue, and it's reported in this issue here in the scikit-learn repo. So if you want to select variables using chi-square, I suggest you use the scipar implementation.
There is a question about a few slides back. So there was like, how did you come up with generated and observed, like with observed and expected table, like this one? Yes.
So you have to calculate the row totals and the column totals. So the row totals here is 60 plus 120, 180. And for female, the column total is 120 plus 92, something 212, I think. So then you put this in this column, it would be 112 times 180 divided the total number of observations. And this gives you 120. Like if you put that in the calculation, this might be true because I did it before putting the slide. And then you repeat.
So this E equals, and then the formula is basically how you compute each cell of this expected matrix, right?
Yes.
Okay, got it.
And then this is cell per cell. It would be this value minus this value squared divided this value plus this value minus this value squared divided this value, and so on. And this is how we obtain the chi-square.
Yeah, thank you.
Okay, filter methods in general share the characteristic that they are independent of the machine learning model. So as you saw, in this case, they are statistical methods that have nothing to do with the models. This is not totally true. And they are based only on the relationship of the feature with the target. So the pros is that they are model agnostic and they are fast computation. The real pro here is that they are really fast to compute because ANOVA and correlation, they are actually geared towards linear models. So they are not completely model agnostic, if you ask me. But the cons of these procedures is that they ignore feature redundancy. And in the extreme case that we have two identical features, they will give the same p-value to the two features. So we will end up selecting both features if they rank high. They ignore feature interaction. So if one feature is not important in isolation, but it is important when combined with another feature, this will not be picked up. And they also ignore model feature interaction. And here is where I said, for example, ANOVA and correlation are geared towards linear models. So if the relationship with the feature and the target is non-linear, this will also not be picked up. So wrapper methods are...
May I interrupt you? Sorry.
Yes.
There is another question related to a few slides back when you showed when to use which methods. So it was like ANOVA, he squared, and so on. And I think there is a question related to that slide. And the question is, which method is the best for categorical variables and continuous target? So I think you said correlation, right? So it's usual correlation like from pandas or whatever.
Yes, for categorical variables and
this is
targets,
like you have
none
continuous
of these methods are suitable.
Yeah,
so
right,
you want to do something else, which is probably some of the things that I'm going to cover later on.
Yeah. And what about when you have like I think you covered like the only one that is left was categorical variable and continuous target, right?
Yes.
And the rest are covered. Okay.
Cool.
Yeah, thanks.
No problem.
And maybe related to the cons that you mentioned, and maybe the answer will actually be wrapper methods. So the question is, like, do you have to do feature selection before hyperparameter tuning, after it, at the same time, or how to do this?
Yeah, this is a question for which I don't have the silver bullet answer. The thing is that some feature selection algorithms are really computationally costly. So if you add a layer of hyperparameter tuning on top, you're going to age and this thing is going to still be running. So at the end of the day, you need to make sort of a trade-off between excellence and the resources of the time you have. So yeah, it's going to depend on your data, on the selection method that you have. Short answer, I guess. It's not
so as a rule of thumb, maybe first get rid of useless features with filter method, and then maybe do hyperparameter tuning. No,
that is one option. If you do embedded methods, you could do everything together because the embedded method is part of the machine learning model. So in that case, you can
what you will talk about next, right?
Yeah. So like I said, it kind of depends. If your data sets are huge, maybe you have no other option than to start with filter methods. If your data sets are not so huge, maybe you can do embedded methods and then you can hyperparameter tune at the same time.
Okay. So let's see what are the wrapper methods. I'm shutting up. Sorry.
Wrapper methods are also known as the greedy algorithms because in the ideal scenario, they try to evaluate every single possible feature subset that you can get from your data. So these wrapper methods will first create every possible feature subset, every subset of 1s, 2s, 3s, 4s, and so on features. On each one of these subsets, we'll train a machine learning model, it will obtain the performance, and then it will select the subset with the best performance. So in the ideal world, this is the ideal feature selection algorithm and should return the best feature subset. This is the description for the exhaustive search. In the real life, with big data sets, even with data sets that have hundreds of features, this is computationally very costly to the point that it is prohibitive. So like it's very, very unlikely that we will end up doing these types of searches. So alternatives to evaluate less feature subsets and then try to make this more computationally efficient are the forward search and the backward search, which instead of building all the possible feature subsets, build a little bit less. And I'm going to talk about the forward search, and I think that after this, how the backward search works is more or less intuitive. So if we have a data set with 4 features, for example, forward search, the first thing that it's going to do is to build a model with each one of these features. It will then evaluate the performance of these models, and it will select the feature that returns the best performing model. In this case, is feature 2. It will then create all possible combinations of feature 2 with the remaining features, like I show here. It trains a machine learning model which with each one of these feature pairs, it returns the feature performance, the model performance, and then it selects the best performing model feature. In this case, is feature 1. In the third step, it creates all remaining possibilities of the remaining features with the 2 that it already selected. It trains a model, it obtains the model performance, and then it selects the best performing trio. And finally, it evaluates the model with the 4 features. Now, this is a very simple data set. We have only 4 features. So here we see that the performance continues to improve. But if we have huge data sets, eventually the performance is not going to stop to improve anymore. So a way to stop the search, because here we need to stop the search at some point, is to stop the search when the performance does not improve beyond a certain threshold. And the threshold, unfortunately, is arbitrary. So it requires a little bit of trial and error. And this implementation is available in scikit-learn. In the MLX10 implementation, we can stop the search when a certain number of features is reached. You say, okay, it's arbitrary. Yes, it is arbitrary, but these algorithms are so costly that at some point you will need to cut a corner. So the characteristics of wrapper methods is that they consider the machine learning model that we want to build, and therefore they consider the feature model interaction, and they evaluate subsets of features. Therefore, they also evaluate feature interaction. On the downside, they are not model agnostic. This means that the optimal feature subset for a random forest may not be the optimal feature subset for a logistic regression, and they are very computationally expensive. So if we end up building various machine learning models, we basically need to do wrapper methods for each one of them, and it's going to take a huge amount of computing resource. So something that is less computationally expensive are the embedded methods. Embedded methods are procedures that are baked into the training or the induction of the machine learning model. So there are models that when they create or find the optimal parameters to match the patterns of the features to the target, that they also assign some feature importance. And so we train the model, we then derive the feature importance, and then we can either remove the non-important features or select the most important features. The classical example of embedded methods is the lasso regularization, because this regularization has the ability to shrink some coefficients to 0. So then we can remove those coefficients. The importance derived from decision trees is also another measure of how important the feature is. And if we consider certain caveats, we can also use the regression coefficients to assign some sort of feature importance. So the advantages of the characteristics of embedded methods is that the feature selection occurs during training the model. So as opposed to wrapper methods, we train only one machine learning model, so they are more computationally efficient. And they capture feature interaction because we are evaluating a group of features, not just one feature in isolation. On the downside, they are limited to the machine learning models that provide some sort of importance about the feature, and they are not model agnostic. So one example where embedded methods is not possible is if we want to build nearest neighbors. So what can we do if the wrapper methods are too computationally costly and we don't have embedded methods for the algorithms that we want to train? Well, there are other machine learning models that we can use. And there are actually quite a few. One that is quite popular is feature permutation or feature shuffling, which is the one that I'm going to describe in the coming slides. Another method is, for example, probe features. Here, what we do is we introduce to the data set 2 or 3 random features, and then we derive importance somehow, for example, from random forests or through feature performance, model performance, and then we select all the features that have higher importance than the random features. We also have recursive feature elimination or recursive feature addition. We have one algorithm that is called maximum relevance, minimum redundancy, that was revitalized by Uber. We have correlation-based feature selection, and then we have some algorithms that are used in specific domains, that, like in finance, which are, for example, selecting features based on the population stability index or the information value. These algorithms are not all present in open source packages, but 3 of them are, and we're currently working on implementing the information value in feature engines. So if you want to watch this space, it's coming soon. So I said I would describe how feature shuffling works. The idea is that if a feature is important, when we random shuffle the order of the values of the feature, this should have a knock-on effect on the performance of the model. So we have a data set again with 4 features. Then we train a machine learning model and we evaluate the performance of this model. In the next step, we're going to shuffle the order of one of the features. We're going to use the same machine learning model to obtain predictions. If this feature was important, we're going to see a massive drop between the performance of the model returned after shuffling with respect to the original one. If the feature was not important, the performance should be roughly the same. Once we assess feature number 1, we shuffle feature number 2. We repeat the procedure, then we shuffle feature number 3, and then we shuffle feature number 4. So by now, we assessed the performance drop that returned shuffling each one of the features, and the final step is to select the features that return the highest drop in performance. Here again, we need to assign a threshold. The threshold is going to be arbitrary, so it requires a little bit some trial and error for data analysis or cross-validation. There are options. So I think that's all about the feature selection methods. If you want to find out more methods, you can find our book or our course on training data. And now I could move to the demo.
Maybe before that, there is a question.
Right.
There is a question about which one of these is your favorite one. So I think the question is like about like whether filter methods should be preferred to wrapper methods or embedded methods, or like how do you decide which one to try? Do you have like a rule of thumb in which order you try different things?
I have rule of thumbs for the datasets that I have worked with. The truth is I've never used filter methods because statistical tests make a lot of assumptions on the data, and chances are the data is not going to follow those assumptions. In particular, the variables more often than not are skewed. So using ANOVA, I mean, we're violating the assumptions of the ANOVA, so it is a risk. And also datasets will have categorical and continuous variables, so there is not really a statistical test that caters for everything in the datasets that I have worked with. So what I normally do is I normally remove constant features. I tend to remove quasi-constant. I remove duplicated. And then depending on how big my feature is, my subset, my dataset is, I will remove some based on an embedded method. And once I have something that is manageable, less than 1,000 features, I would say, I will try recursive feature elimination that I did not describe in this slide, which basically ranks features based on the model performance. Sorry, ranks features based on the importance derived from an algorithm. And then it starts by removing the less important feature, trains a new algorithm, sees if the performance dropped. If it didn't drop, then it removes this feature and tries the second one. If the performance didn't drop, it removes this feature and tries
this is like backwards elimination or something like this, right?
Yes, it's recursive feature elimination. So that's the one that I've used the most. But this is because of the nature of the datasets that I have worked with. For example, for microarray and drug screening, where variables are normally continuous and you have like so many features, what they do is they do filter methods because they have no other choice. Everything else is computationally impossible.
Okay.
Wrapper methods I have not seen implemented, I have to say, because of the cost, for example. So I don't know if that answers the question.
Yeah, let's take a look at the demo and then we will come back to the rest of the questions.
Okay. Can you see now my Jupyter?
It's very tiny though. Like if you can make it like, I don't know, 5 times larger, you probably have a very large screen.
Yes, I do.
Can you make it a bit larger again?
Larger than this?
Yeah. Like on a laptop, it's not really visible. Okay, that should be okay.
Okay, let's try something different then.
And while you're trying this, there is a question, what does shuffling mean? I can try to answer this and you will correct me if I'm wrong. So reshuffling means you do not remove features like somebody suggested, but on the contrary. So you keep the feature, but you just randomly reorder values there. So let's say you have 1, 2, 3, 4, and then after random shuffling, you would have 3, 4, 2, 1, for example. So values will be arbitrarily changed within the column only. And you keep doing this for every column. Did I get it right?
Yes, correct.
Okay.
So how about now?
Yeah, maybe like one more time, like Control plus one more time. Okay, that should be enough.
All right, so if you go to the repo, the Data Talks Club repo, you're going to see 4 notebooks that describe some of the methods that I talked about today. So if we go into the constant features, all right. So in this notebook, what we're going to do is we're going to remove features that have low variability. And we have basically 2 implementations available. We have the variance threshold from scikit-learn, and we have drop constant features from Feature Engine. And they work a little bit differently. Variance threshold calculates the variance of each feature. Therefore, it only works for numerical variables. And it will remove features that have a variability below a certain threshold. The default threshold is 0, which means that by default, it will remove constant features. But if you also want to remove quasi-constant features, you need to play a little bit with the threshold to try and get more or less what you want. So let's carry out first with the variance threshold, and then I go into the details of how drop constant features work. So this one here is just, I'm creating a toy data set, so this is not crazy important, but this function comes from scikit-learn. So here I'm creating 1000 observations, 10 features, binary classification, and then I am basically arbitrarily saying that features 5, 0, and 9 are 1. So I'm creating artificially 3 constant features, which are these ones that you see here, 5, 0, and 9. They all have the value 1. Then I'm going to separate the dataset into train and test, utilizing the train test split function from scikit-learn. Here I pass X and E, are the ones that I created here. And this is to tell to get 30% of the observations in the test set. You're probably familiar with this. So I'm kind of moving ahead. And the variance threshold from scikit-learn, we basically use it as we would use any model from scikit-learn. For example, random forest, we just initialize the transformer, and here we indicate a threshold of 0. This will remove constant features. So then when we fit it to the train set, and here it's important to fit the data to the train set to avoid data leakage. We want to keep the test set basically naive to all of our manipulations. So when we do fit, this will identify all the constant features. The get support attribute or method returns a Boolean vector with true and false for the features that will be selected. So here, if we add over this Boolean vector, we get 7 because 3 of our original 10 features were constant. So it will select the ones that are not constant. And here we can get the names passing the get support to the columns of the original dataset. And here I'm negating the get support so that I get the constant features, which are the ones that I created artificially at the top. Scikit-learn recently implemented the get feature names out. So if you train it over a pandas data frame, now you are able to obtain the names of the features in the resulting data frame. So this could be the non-constant features. And to remove the features from the data, we just do selector transform, and we pass the train set, and now we also pass the test set. And if we corroborate the shape, you will see that now we have 7 features instead of the original 10 features. The thing with scikit-learn is that it returns NumPy arrays, so we need an extra step to convert this back into a data frame, unless we're happy with NumPy arrays. So this is what I'm doing here. I am converting this array into a data frame, and then I pass the names of the remaining features, which I can get with the method getFeatureNamesOut from the selector. And this is the resulting data frame without the constant variables. Drop constant features from Feature Engine works a little bit differently because it does not use the feature variability, it uses the unique values of the feature. So for the case of constant features, the functionality should return the same output, but for the case of non-constant features or quasi-constant features, they work a little bit different. Here, drop constant features takes the parameter tolerance, and here we say tolerance 1 means that if the feature has the same value in 100% of the observations, drop it. But if we put lower values here, like 0.95, what we're telling the transformer to do is to drop features that have the same value in at least 95% of the observations. So this is fairly intuitive, what the transformer is doing. We don't need to make any guesses about the variability. And the beauty of drop constant features is that because it does not work with variability, it works with unique values. It can be suitable for both numerical and also categorical variables, even before encoding the variables into numbers. So this drop constant features is very practical for a very first screening to remove all constant and quasi-constant features. The procedure is then identical because Feature Engine adopts scikit-learn functionality. So we're going to fit the transformer to the train set. This should find the constant features. The constant features are going to be found and stored in the features to drop attribute. So here, if we execute this command, we're going to see the 3 constant features that we determined at the beginning. And then with transform over the train set or the test set, we remove the constant features from the data. And if we can corroborate it, and we can corroborate it with the shape, and we see that we have 7 features. And another beauty of Feature Engine is that it returns automatically pandas data frame. I say it's a beauty because I'm the maintainer of Feature Engine, so I couldn't say otherwise. Okay, so that's it for this basic method. Let's say we want to do ANOVA. ANOVA is provided out of the box by scikit-learn. I'm going to implement ANOVA. As I said, we need continuous variables, classification target. So I'm loading the breast cancer dataset where we have characteristics of tumors, and we want to predict if the tumor is benign or malignant. And from scikit-learn, we're going to use the F-classif. F is for the F-score, and F-score is the ANOVA statistic that follows the normal the F distribution. That's going to basically give us the probability of the null hypothesis. This is too much statistical jargon, that's why the name. And then so F-classif, what it's going to do is it's going to assign p-values to each one of the features. And then we need another transformer to select which features we want to keep. And there are a number of options. We can select the top k features, where k is an arbitrary number, for example, the top 10 features. Or we can select, this one is called false positive rates, which means that we're going to select all features which p-value is above 0.05. This comes from traditional statistics, where we are normally happy to refute the null hypothesis when the probability is 5 in 100. For huge data sets, this may also mean that there is actually no difference, because remember that big data samples inflate the p-values. Moving on with the demo, so this cell basically loads the breast cancer dataset. Here we have the variables. I'm making a histogram to kind of understand the distributions of these variables and see if they, first of all, are continuous, so that I can use ANOVA. For this data set, they are continuous, so that's no problem. And then if they are normally distributed, and here I can see already that there are variables that are not normally distributed. So the p-values returned for these variables like perimeter error or area error. I'm not sure you can see the arrow on the screen. The values of the ANOVA may not be completely reliable. But for the sake of the demo, I'm just going to proceed. F-class-if is a function. It takes the train set and it takes the target, and it returns two arrays. The first array is the F value that I didn't have a chance to describe, but it's basically the ANOVA statistic that follows the F distribution, and the one that is going to help me obtain the p-value, which is what I get in the second array. And the p-value is the probability of the null hypothesis. The smaller the p-value, the more predictive the feature, in short. So I'm going to take this second array here, and I'm going to convert it in a pandas series. In the index of the series, I'm going to add the features. I'm going to sort them in ascending order, because remember that the higher the p-value, the less important the feature. And then I print it here. So what we see is that most of the features have a very small p-value, and there are these three features that have a huge p-value. So there is one thing that we can absolutely say for sure, is that these three features are irrelevant, because in a big data set, if the p-value is bigger than 0.05, then we're happy to remove those features. But for the remaining of the features, it will depend. We will also have to basically evaluate the shift in the mean and so on. This is what I'm going to do here later. So here I'm going to plot the distribution of this feature that was really important when the target is 0 and when the target is 1. And here what we see is that the smoothness for malignant tumors is worse than for benign tumors. So, makes sense. The p-value here with the distribution of the tumors across the distribution of this variable across the two types of tumors. But if we take a feature that was not important, then we can see that the two distributions kind of overlap, which is more or less what I expect. So I'm kind of happy to say that ANOVA seems to have worked okay here. So this so far ranked the features. Now I need the next step, that is to select the features. So in this example here, I'm going to select the features which p-value is smaller than 0.05. This is what this select FPR is doing. So I pass the ANOVA ranker, to call it somehow. I indicate the threshold, and then I feed it to the train set. And then all scikit-learn transformers share the same functionality. With get support, I can get the features that will be selected. And if I pass this Boolean vector together with the columns of my dataset, I obtain the names of the features that will be retained. Another way of doing this is by using the get feature names out. And with transform, we reduce the dataset. So we will remove all features whose p-value was bigger than the one that we determined here. And then again, we need to convert it into a data frame and add the column names. If we instead want to select the top ranking features, we can use select k-best. This works exactly the same way. We pass the ANOVA ranker, and then we tell them how many features I want to select. This is arbitrary. It could also be optimized with cross-validation. And then we feed it to the train and the tester. And the rest of the procedure is identical. So now we can move on to an embedded method. This one is one that I would actually recommend if you're into linear models. I'm going to work on a regression model here. So I want to pick up the California housing that is going to predict house price based on a number of attributes. Select from model is going to select the features based on the ranking attributed by the lasso regression. And here I also import the lasso regression. And very important, linear models are susceptible to the scale of the features, so I need to put the features in the similar scale. That's why I import the standard scale.
So and there was just a question, if we need to normalize features before doing feature selection. And I guess the answer is it depends, right? And it depends on what kind of technique we use. And for this particular one, we need to normalize them.
Yeah, correct. If we're using methods for trees, we don't, for example. For the filter methods, we also don't, because they are evaluated individually. Chipping in as it comes to my brain. So here I load the data set. This is not important. Here I set up the scaler. I feed the scaler to the train set. And now all the logic of the feature selection can be summarized in one beautiful line of code where I use the select from model that comes from scikit-learn. I pass the lasso with some parameters. This is the penalty, and this is the random state. And then I feed the selector to the scaled form of the train set. And the important things here is that the higher the penalty, the less features that I'm going to select. So where do I put the penalty? Good question. This is something that we can optimize with cross-validation, for example. And the rest of the functionality is identical. It will always provide the get support that returns true for the features that will be selected. And then we can use it together with the columns of the data to find the features that will be selected. And here what I wanted to demonstrate is that the selected features, okay, so this example is a bit silly because I didn't select any feature. So I need to increase the penalty bit. Let's see if we can play this one. Yes, now I removed one feature. So we have 8 features. It selected 7 features. It means that this particular lasso with this particular penalty reduced the coefficient of one of the features to 0. And here, this is what I'm basically showing. I am picking up the estimator, the lasso. I am finding the coefficients that it attributed to each one of the features, and I'm finding how many it shrunk to 0, basically because I want to corroborate that scikit-learn select from model is doing what I think it should be doing. And sometimes this is good practice. So yes, this is the thing. And this is important because select from model doesn't work identically for all the selection models. So for lasso, it will select features whose coefficient is not 0. But for trees, it will select features whose importance is bigger than the mean importance of all the features. So careful with that. We need to, this is explained in the documentation. And then with transform, we basically reduce the data to the selected features. And then the last one is an implementation of feature engine for feature shuffling. I can go over this one very quickly because we're running out of time. I'm going to use the bread cancer. We need to train a machine learning model, so I'm going to train a random forest. And then from feature engine, I will import the select by shuffling. So here I load the data. The important thing is here. First of all, I need to instantiate a random forest with some parameters. And then I will instantiate the select by shuffling. The select by shuffling takes the random forest, takes the metric to optimize, and this is important because sometimes we want to optimize one metric, sometimes we want to optimize the other one. The threshold, so here I'm saying that I will select, or in other words, I will drop all features. Basically, I don't want to drop any performance. So if a feature drops a tiny bit of performance, I want to keep it. This is where I'm telling with threshold equals 0. And here we do this with cross-validation. So with fit, this algorithm is doing everything that I described on the slide out of the box. It stores the performance of the model with all the features without shuffling. And in the performance drift, it stores the drop in performance of all the features. So for example, this feature is super important because when we shuffled it, it dropped the performance of the model dramatically. These features here have a negative performance drop. That means that we shuffled, and it basically doesn't really make a difference. The features that we're going to drop are stored in this parameter. And then with transform, we can remove the features very easily from the data. So yes, I think that's it for today. And if you have more questions, maybe we can tackle them now.
Yeah, maybe it will be easier if I just share my screen because there are quite a few questions. So the first question is, could you mention feature selection methods for time series data or packages maybe?
Yes, good question. The thing is with time series data, if you were in Kishan's talk, what some of the methods do is basically we take the time series, we derive a lot of features, and we convert that time series into tabular data. And once we have tabular data, then we can implement any of the feature selections methods that I described today. So the key thing for time series is to basically first create the features. And once we have a representation that is similar to the tabular data that I covered today, then the feature selection methods are the same.
And I guess it's pretty important because like when for time series we generate a lot of features, then many of them could be quite useless, right? So you want to kind of discard them.
Yeah.
Okay. So what about feature selection for deep learning models when you have a lot of features?
The thing about deep learning model is that more data is better. So I'm not familiar with a deep learning model where we actually want to select features. We want to give the model as many features as we possibly can and as many observations as we possibly can, and we want to let the algorithm do its magic. So feature selection is mostly geared to tabular data and off-the-shelf machine learning models.
But I guess here it could be that, let's say if 500 out of 1000 features are useless, it doesn't matter if you put this into a deep learning model or something else, it will still be useless, right? So maybe like I guess you can just use cross-validation to figure this out, right?
You can. Training a network is really costly, and if you add cross-validation on top, it will take forever. I think Andrew and G machine learning course is really useful in this respect because we basically ranks the performance of the different models based on the number of features. And when we have features in the realm of 1,500, off-the-shelf models like gradient boosted machines work equally well than deep learning. So it makes no sense to be deep learning models. We are just making something that is really complex when we could resolve it much easily. So yeah, like I would not do it. I guess that's the point.
Okay, and I guess this one is indicating that it's the same question split into multiple, because in Slider there is a limit on how long the question could be. So I hope they all belong together. Let me try. So removing features based on variance is based on the premise that more variance means more predicting power. However, in the presence of extreme values, variance is going to be high. Wouldn't variance-based feature selection introduce noise in the model instead of contributing to better predictions?
Yeah, it could. It could. That's why I said that in principle, we assume that more variable features are more predictive, but it could also be that even without outliers, the variability of the feature is not predictive. So this is something that we need to check. If this variance selection is mostly geared towards removing those features with low variability, more than selecting features with high variability.
I assume that we are doing linear regression to use backward elimination. Then how do we decide which variable we remove first?
It depends on the implementation of the backward elimination. If we're talking about backward elimination, okay, so here is a subtle difference between backward search and recursive feature elimination. So I don't know how to tackle this question. If we're using recursive feature elimination, we're going to rank the features somehow. Scikit-learn will rank them based on feature importance, derived from lasso or derived from trees. And then it will remove the less important feature. Then it will train another model, it will rank them again, and then it will remove the less important feature. I think this answers one question. Feature engine does something different. It ranks the features based on feature importance, but then trains the model and assesses model performance. If the performance drops when I remove the feature beyond the threshold, then that feature is kept. If the performance doesn't drop, then the feature is removed. So there are different implementations.
Yeah, they sound very similar actually. So the difference in one case that we always remove feature, but it's just with the least like the least useful one, and in the second case we remove features only if its usefulness is less than a certain threshold, right?
Almost. In the second case,
Almost.
we
Okay.
are evaluating the feature based on the performance of a model that we train on the subset.
Uh-huh. Okay.
Scikit-learn evaluates the feature based on the importance derived from the model. So scikit-learn will always evaluate that based on lasso, for example, so coefficient magnitude or information gain, whereas feature engine will evaluate the feature based on the ROC you see or the accuracy or the medium square error.
Okay, I think I got it. So next one, is there any link between the number of features and the data size, for example, number of rows? Thanks.
I think, what you mean by number by link? I think
Yeah, I
you get
guess
what
it
you get,
depends,
no?
right?
Yeah, you get what you get. The thing, okay, so some things that I don't know if this is where it's going, but if we have more features than observations, then this affects the performance of models more often than not, particularly for linear models, and also true for trees. So I guess this is the only link that comes to my head.
So how many questions can we take now? I don't know if you need to go or you have a couple of minutes.
No, I'm okay.
Okay, so I don't know, let's try to answer some of them. Do you have any Python package for material or material for feature selection in time series? I think we covered that, right?
Yes, I think so.
Shuffle, permutation, feature selection, scikit-learn, right?
Scikit-learn has a permutation importance function that returns the importance of the features based on permutation, but it does not select out of the box. Feature engine adds on top of that the selection procedure.
But I guess here question is whether shuffle and permutation in this case are synonyms, and I guess they are, right?
Yes, they are the same.
You said that big data exaggerates small p-values for statistical feature selection. Is there a rough estimated size of the data set when it becomes an issue?
Yes, I would say 100 observations. So,
100. Okay.
Yes, statistical tests were originally designed for small sample sizes. I mean, statistical tests are very ancient. Big data is a very new topic. So I would say it will affect most of the data sets that we're going to work with. There are formulas to calculate the importance of the sample size based on the difference that we want to pick. I think that's a little bit over the top to select features, but if it is very important because we also want to understand the feature and the value, etc., then there are formulas to calculate the effect of the sample size.
Okay, we will not repeat the time series related question. You can just go back and rewind the, it's all recorded, so you can just go back and check it. So breast cancer data feature selection methods, are we accounting for correlated features? Which one of them? It was like the second one, ANOVA, right? Or which one was it?
Based on the authors of Lasso would account for correlation. And to some degree, if we use 3 derived importance, it should also contemplate correlation. It all depends on the thresholds that we're using, the penalties, and so on. So, yeah, there's no simple answer to that question. I guess correlation is important to some degree. There is always going to be some degree of correlation in the features. If they still return a good performing model, then we don't care too much.
So, but this one, like Lasso, you were saying it was California housing. I think the question was about this breast cancer data, which was, I don't know, do you remember one? What was it about ANOVA or? Because in ANOVA you said, was it like when you use filter methods, they don't really care about if it's a duplicate feature, they will assign the same p-value.
Oh, okay. Yes, filter methods, because they evaluate each model individually. If two features are identically or highly correlated, they will select them both. Now, I guess the way I understood the question is, do the other methods, because these methods certainly, filter methods certainly do not account for correlation. Now the question for me is, do the other ones account for correlation? And the answer is yes, to some degree, depending on the penalty and depending on the number of features and the thresholds that we use to select. So if we want to be absolutely sure, we should evaluate them.
It also becomes tricky, like for tree-based models, like if we have correlated features, then importance becomes funny, right?
Yes,
okay, does
exactly.
lasso work well in presence of nonlinear covariates? What happens when we are interested in outliers, for example, and find nonlinear relationships?
Yes, no, lasso is a linear model, so it will not work if the variables are not linearly related. That's one of the assumptions of linear models. So this will only be suitable for linear models. If we don't have a linear relationship, what we can do is we can modify the variables so that they are linear as much as possible. And there are ways to do so. For example, we can discretize the variable and then use monotonic encoding, or the weight of evidence, for example, that's used in financial institutions. We can transform, if we want to overcomplicate things, the features with a decision tree, and now we sort of create a monotonic relationship. So there are ways to make a nonlinear relationship linear by feature engineering. It will also return features that are less interpretable depending on the method that we use. To answer that question, but yeah, it's not suitable. I guess it's the answer, the short one.
Okay, yeah, maybe this one is a bit packed. Use lasso with select from model and trees with permutations shuffle. What about recursive feature elimination and sequential feature elimination? What to try first?
Sequential feature elimination, I guess they are referring to the wrapper method from scikit-learn. If I remember correctly, that's the name of the class.
No.
What to try first? I don't think there is, you could try both. I would try them both in parallel, in fact. Sequential feature elimination, if you have a lot of features, is going to basically run forever. Don't know if it's computationally possible. So I guess I would go for recursive feature elimination because it's the most computationally efficient alternative.
Okay. Well, oops, I accidentally marked it. So the question was something related to PCA, probably. If you perform feature selection using PCA, what are the basic disadvantages compared to lasso?
The thing is, like I said at the beginning, PCA is not a feature selection algorithm, it's a dimensionality reduction algorithm. So PCA is going to create principal components, and that principal component has a dimension for each feature. So say if I have 1,000 features, then my principal components are going to have 1,000 dimensions. And then basically I also end up with 1,000 principal components, but then the thing is that I will select the first 10. But to build each one of the first 10 principal components, I still need my 1,000 features. So I didn't reduce the problem. I still need to deploy 1,000 features, and then eventually I still need to maintain a model with 1,000 features, except that the only difference is that the model will consume 10 principal components. So the model will be simpler, but the entire machine learning pipeline will not be simpler. It will be complicated. So from a deployment perspective, it's complicated. And then when we have to interpret those models, it's also complicated because
yeah, it is.
Yes, like it's hard to say what each component is at the end of the day.
Okay, I think that's we managed to actually cover everything. We needed to stay a bit longer, so thanks for spending a bit of time with us to answer all the questions. Highly appreciate it. Thanks everyone for asking questions, a lot of interesting questions. And yeah, check out the GitHub repo. The link is in the description. I put it there. So all the things you saw in the demo are there in GitHub repo. And then you have a book, right, about feature selection. So if anyone is interested in learning more about this topic, so I think I saw the link in the GitHub repo, right?
Yeah.
Okay. I guess that's all for today, right?
Yeah, okay. Thank you then.
Okay. Goodbye, everyone.